Welcome to video 25 on the TTB course. This video is from part 5 of the course. In part 5 we introduce a set of TT platforms. We then illustrate how these platforms can be applied using a range of case studies. In this video we will consider the development of a steering column lock for use in a passenger vehicle. The material in this video is based on chapter 25 in the ERES2 book. The video provides only a summary of the material that's presented in the chapter, and I suggest that if you haven't read the chapter already, you should stop the video now, read the book chapter, and then come back to the video. In this study, we're considering the development of a steering column lock controller, SCLC, that is to be used in a high-volume passenger car. We will assume that members of the development team already have a good understanding of the system requirements. Our goal will be to explore ways in which we can meet these requirements using 4 different TT design options. Each of the design options will employ azo decomposition. So let's just first look at the locking mechanism that we're going to employ. So our locking mechanism involves putting a locking bolt into an appropriate hole in the steering column. So we have 4 core components listed on here. So we have the locking bolt itself, which can be moved into and out of the steering column. We have the steering column itself with holes into which the locking bolt can be inserted. And we have 2 switches, limit switches that are triggered when the locking bolt is fully in place, and a limit switch 1 which is triggered when the locking bolt is fully withdrawn. So when the lock system is locked, limit switch 2 is in place. I should make it clear that there are 2 channels, 2 independent channels assumed on each of these limit switches. So limit switch 2A and 2B are 2 independent switches that are both set when the lock is in place. Limit switch 1A and 1B are both set when the system is fully unlocked. There's a situation when we're unlocking when neither switch is set. So neither switch is depressed during the unlocking operation. Similarly, during the locking operation, there's an interval when neither switch will be set. To move the locking bolt, we have a DC motor. And to control the DC motor, we have an H-bridge arrangement. This will be familiar to most people watching this video, I assume. So the H-bridge consists of 4 switches, A1, A2, B1 and B2. If we close A1 and B2, the motor moves in one direction. If we close A2 and B1, the motor moves in the reverse direction. If we close A2 and B2 or A1 and B1, we have a short and potential for sparking at least, and potentially even a fire in the steering column. So this option is of course to be avoided. So we're aiming to provide control of these switches in order to drive the DC motor in a forward or reverse direction. So there's one key hazard in this design that can be easily identified. This is that the steering column is locked while the vehicle is in motion. So this gives us functional safety requirement 1. If the locking bolt ever leaves the unlocked position while the vehicle is in use, the steering column lock controller shall ensure that the steering column lock controller motor control is disabled by opening switch A1, A2, B1 and B2 before free movement of the steering column is impeded by the locking bolt. This is a key safety requirement. So we need to be able to detect that the locking bolt is moved, and we need to be able to react before there's any risk that the locking bolt can actually lock the vehicle, if the vehicle is ever in use. So as noted at the beginning of this video, we're going to assume that our controller is developed in compliance with ISO 26262, and we're going to assume that our functional safety requirement FSR1 has been assessed as being of automotive safety integrity level D. We'll further assume, again through a process of azo decomposition, that we wish to decompose this single functional safety requirement into two new FSRs, FSR1A and FSR1B, each of which is at azo BD. So we've met a decomposition like this in previous videos. So again, we're assuming that we're going to reduce costs by applying azo decomposition in this way, and our expectation is that we'll reduce cost without compromising the safety of the system. To justify this type of azo decomposition, the two new FSRs must be implemented independently. And it must be possible for the development team to demonstrate clearly and unambiguously that the two implementations are independent. So there's a couple of options, and again we've touched on these options in previous discussions. We can allocate FSR1A and FSR1B to different processors. In this case it's probably easier to argue that this is a safe solution, but there will be concerns about costs. Option 2, we can allocate FSR1A and FSR1B to the same processor. It's likely that costs will be lower. The question is whether we can meet the safety requirements. We will consider variations on both of these options during the remainder of this video. So we're going to create two independent task sets, and we're going to do so in this example in a little bit more detail than is possible in some of the previous examples. So we're assuming that each task set, even where we're running on the same processor, we're assuming that each task set will employ different sensor inputs. So we have independent sensor inputs for each task set and independent outputs for each task set. So if you refer to the ERES2 book in chapter 25, you'll see a greater discussion about the detailed organization of the task sets. So these are, in the form of a context diagram, an illustration of the inputs and outputs to our task set. These are the two task sets. So for example, in task set 1, we read current sensor A. In task set 2, we read current sensor B, and so on. So we have different sets of tasks and with as high a level of independence as is possible. These are discussed further in chapter 25 of the book. Here I want to focus on the high-level decision about the design options. So our first option, and one that is likely to be an obvious option in an automotive space, is to use a single microcontroller, probably in this case an azo D microcontroller, and an external watchdog controller chip, and control the system in this way. So we're using azo decomposition, two task sets on the same microcontroller, and an external watchdog controller to deal with scenarios in which we detect a failure on MCU A. Our second option, of course, is to use two separate microcontrollers to do this. Again, personally, I'd have a higher degree of confidence in this dual microcontroller arrangement because we've got a greater level of protection against common cause failures in this type of design. So now we're using two microcontrollers, probably azo B microcontrollers, which themselves would be of lower cost, and we're giving the microcontroller B, for example, control of these two switches, so that, for example, if microcontroller A fails completely, then microcontroller B can still completely disable power from this system. By disconnecting A1 and A2, we remove power from the system and this motor will stop moving. Different combinations of switches would not give us the same level of control here. So a single microcontroller can disable the motor, and a single microcontroller, if it still has control of both switches, can prevent a short in the system as well, if we use this control setup. there are other constraints that we need to consider. We've implicitly assumed in the discussion so far that we're going to use discrete switches, A1, A2, B1, B2, to implement our H-bridge. In practice, we probably wouldn't do this. A single H-bridge driver chip is likely to be used instead, because this will be cheaper. If we use an integrated H-bridge component, then we may have to treat this as a single point of failure. If we do that, then this raises some further questions about the two designs that we have. So if we go back and look at design 1 again, we have the P1 power switch available. So this should give us a means of removing power from the motor if the H-bridge fails. So this design 1 still remains acceptable if this is an integrated H-bridge component. In design 2, we don't have the same level of flexibility. So we've duplicated our processors, but if this is now an integrated H-bridge, then this design is less attractive. And our design may not be as robust as we had intended. So we need to make some changes here. So in design 3, we're assuming that we have an external watchdog controller, and that for this to be operational, it requires a dynamic signal from both MCU A and from MCU B. Without the dynamic signal from both of these microcontrollers, the EWDC won't function and this switch will be opened. So this gives us a means of disabling the H-bridge should this be required, and now we have 3 independent processing elements in here, and as long as one of these 3 elements is functional, we will be able to disable power from this system. Let's consider one other option. We've discussed the need for and the implementation of limp home processor modes and limp home platform modes in several videos on this course, and we've tried to demonstrate that such a feature is useful even in simple household goods such as a washing machine. So in the washing machine example, not in the video but in the book, we discussed the possibility that we would use a limp home mode in the washing machine to allow the customer to drain the drum in the event of a problem. This would mean that the customer didn't have to prise open the door and be left with a large puddle of water on the floor in the event of a failure of the washing machine circuit. So we were using a limp home circuit there to provide an ability to give us useful behavior that would prevent possibility of further problems for our customer. In this case, in the case of the steering column lock, we're going to consider a safety-related solution here. I think before saying this, it's worth noting that the safest way of building the steering column lock controller is to not incorporate a steering column lock in the vehicle. This is clearly the safest solution. What we're implementing here is a security feature, and we're adding a security feature to the system, in particular to prevent theft of the vehicle. What this example illustrates in one way is that sometimes there is a conflict between security and safety in the design of embedded systems. This is not always appreciated. Some people assume that by making the system safe, we're making it more secure. By making the system secure, we're making it safer. It's not always the case. There are sometimes conflicts between the requirements for safety and security as we develop this type of system. In this case, if we return to the particular example, in this case, let's assume that it's possible that during the operation of the vehicle, we find that the steering column lock has been engaged. Further assume that this might happen. It's conceivable that this could happen when we were in the middle of the fast lane of a motorway, for example. In those circumstances, it would be particularly important to try and find a way of reversing the steering column lock to remove the bolt from the steering wheel so that we could safely bring the vehicle to a stop. So if we're going to do this, we're going to have a limp home platform mode that's going to allow us to unlock the vehicle. That's our goal. So this may sound very sensible, but we should make it clear that this would not be a trivial design challenge. Great care would need to be taken in practice to ensure that the increased complexity that resulted from the addition of this design feature would not result in an overall decrease in reliability. One reason for this concern would be that incorporating any form of redundancy in an actuator system, such as a steering column lock, is as a general rule much more challenging than a design that involves duplication of sensors. Actuator duplication is very challenging. I mean, just imagine controlling a steering wheel. If your motor for turning the wheels of the vehicle jams, it doesn't really help you very much if you've got another motor available. If the wheels are already jammed, what can you do? Similar challenge applies here. How are we going to safely ensure that we can actually unlock the vehicle? What we will assume here is a common design solution with motors. We're going to assume that we have a second set of windings available on the steering column motor, and we will employ a warrantor unit to control these windings in the event that we find that the steering column lock has been engaged. So if the warrantor unit detects a problem, it will try to remove power from the original control system and trigger an unlock operation by means of the second set of motor windings. So given these design options, which one should we choose? It's rarely easy to identify a single perfect design solution in these circumstances. However, we can narrow down the options. For completeness, we considered one design with a reversing option, design 4. In practice, the complexity and cost of this design would mean that it was unlikely to be selected. Instead of doing this, I would prefer to have a comparatively slow moving steering column lock, so that we have time to detect if the steering column locking process has begun. I would suggest that would be a more practical option than trying to have a fast-moving steering column lock and then try and deal with the situation if we ever find that it's locked when it wasn't intended to be locked. If we accept this, then we're therefore selecting between design 1, design 2 or design 3. If, as seems likely, an integrated H-bridge driver chip is used, then this may further restrict our design to design 1 or design 3. On technical safety grounds, design 3 wins, at least as far as I'm concerned, because it offers greater protection against the risk of common cause failures. In the automotive domain in particular, cost concerns will clearly be a factor. Design 1 is likely to be cheaper, and we would have to explore carefully whether this is safe enough to meet the needs of a particular application. That would require careful study. So what we've tried to do here in this study is illustrate how some of the platforms that we presented in previous videos can be used to allow us to explore very quickly a set of potential design options for a non-trivial safety-related embedded system. The design platforms don't, of course, say that result in a situation which says this is a perfect design and you must use this one. What they do is they give us a means of quickly exploring a range of possible design options, and then we need to consider the precise needs of a particular application in order to select an appropriate solution. That brings us to the end of this video. Please read Chapter 26 in the ERES2 book before you continue with the course. Thank you for watching.